Ciao, come va? That's all Italian I know. So I am Francisco Fernández. I'm from Madrid, Spain. I work in a small startup called Upclose.me. We do live video streaming. I also run C++ user group there. And if you want to reach me, here you have my email and my Twitter handle. You can complain about the talk, ask whatever you want. And below you have a link to these slides. So if you want to go there and download it, you can do it. And today I'm going to talk about garbage collection in Python. I'll speak about garbage collection also in Python and CPython and PyPy. That are the two main implementations that I know. And why I did this talk? Well, in first place, I really like to dig deeper into things. I really like see how things work. So I started to see Python code, and the other reason was that a few months ago we had a memory leak that all the times, 90% of time is your fault and 10% is a bug. So at least was my fault. And that was the reason why I did this talk. So this is the overview of the talk. In first place, I'll introduce why do we need garbage collection, or why it's good to have garbage collection in our language. Then I'll explain you a little bit about some academic concepts, because this topic started in academia, as almost everything. And then we will explore the two main implementations of Python, CPython algorithm, and PyPy 1. OK, so let's start. What's the motivation? Why do we need garbage collection, or why is handy? Well, if you have ever programmed in C, C++, or even new languages like Rust, managing memory is a hard topic. You have to think very carefully how to write your code. Also, you need to know more about the system you are writing for code. For example, you need to know the difference between a stack and heap. You need to know differences between operating systems. And also, we have some very well-known problems if you have ever programmed in some low-level languages. Like, for example, ownership of resources. For example, here, let's say that this is a very simple example, but we can consume a library that returns a pointer. In first place, we don't know if it's allocated in, well, it should be allocated in the heap. But we don't know if we are responsible about freeing this resource or the library itself. So this can be a huge problem. Other problem can be the dangling pointers. In this case, we are allocating a resource, a variable in the stack, and we return a reference to this variable. But when we are out of this scope, this value is not valid anymore. It's trash at that moment. So there are lots and lots of problems with dealing manually with memory. Okay. So here we have John McCarthy that came to the rescue. He implemented in the 60s the first garbage collection algorithm that was mark and sweep for Lisp programming language. And I needed an excuse to put this photo. It's awesome, be playing with chess with the computer. And let's start with some academic concepts that we have to know to understand a bit about garbage collection. Okay? Oops. Okay. Sorry. We need to know what is the heap. The heap basically is a data structure where our objects are allocated or delocated. So basically, it's the space in memory we have when our object lives. They live there. Then we have the mutator, that the academic definition is the part of a running program which executes application code. Basically, it's our code that asks for more resources. It doesn't use anymore, so the mutator is basically our code. And finally, we have the collector, that the academic definition is the part of a running program responsible of garbage collection. In our case, this part will be on Python implementation, depending on which one we're using it. This will be our interpreter. So what's the definition of garbage collection? Garbage collection is basically automatic memory management. And here we have some fancy definition that says that while our program runs, or the imitator, it allocates memory. So we are allocating some, for example, in Python, object instances, and this is allocated into the heap. So if we reach some point that we don't have more memory, or depending on the implementation, we need to free resources, the collector reclaim this unused memory. Okay? Pretty simple so far. So now that we have the tools, at least the theoretical tools, we'll see the different implementation we have in the Python world. Okay? First place, I'll start with C Python implementation that implements, it has a garbage collector as far as we know. And the algorithm that it implements is reference counting, also with a cycle detector. We'll see later what is a cycle in garbage collection. And for detecting cycle has some kind of generational algorithm. Okay? I don't know if you know how Python is implemented in C Python implementation is how objects are implemented internally at C level. If not, here you have the main abstract, that is the Py object, that basically what it has is a counter. Well, I think probably I should explain before how reference counting works. Let's imagine that we have this simple program. We have a list, and each object in C Python has a counter of how many references has this object. So, for example, here we have a list that is referenced for the interpreter. So, at least this counter will be 1. Okay. Now we declare a class capital A. Okay, and again, as far as you know, a class is also an object. This will have this counter will have a value of 1. Now we instantiate a class. Again, this counter will have 1. But now my list will append. I am appending the instance of A to my list. So now the counter is 2 on the object A, because now at least 2 objects are referencing this instance. Okay, so here is the counter that I'm telling you. It has the count of how many resources referentiate this object, and we do that. Well, Python does it for us underlying, so we don't have to take care about incrementing or decrementing this counter. C Python does it for us. So once we, for example, here we have a chunk of code of list object. This is C code, and here this line is the one who takes care about incrementing this counter by 1. When we insert to some list 1 element, the implementations take care about incrementing this counter. Okay, so it's go incrementing. So this is the macro expanded. Basically, what it does is, given the struct that I showed you before, it increments by 1. Nothing difficult. But when these resources are freed, well, once we stop using these objects, this counter is decremented by 1. So, for example, now my list doesn't hold anymore this object A. So what does C Python internally? It decrements this counter by 1 using this macro. Don't scare. See? And if the counter is 0, what it does is deallocate this object. It's not used anymore by anyone, so it deallocates the object. Seems easy, right? I'll show you now in a graphic way, because I think it's easier to understand in that way. Let's say we have some object in our runtime, okay? And a new object comes to the scene, the object A. And this object is held by C. what's the value of this reference count? 1. Let's say that another object comes to the scene and also referentiates A. Now the counter is 2. But these objects are not interested anymore in A, so they start the referentiating A. So as you notice, the counter is 1 less than before, and C is not interested anymore in referentiating this object. When it reaches 0, done. This object is deallocated. Okay, easy. But for me, it seems too easy, right? We were missing something. No? Yes, we are missing cycles. What happens if two objects referentiate themselves, like in this example? I am creating a cycle in our graph. So it's something like this. Okay, we have two objects that referentiate to itself, and if C is not interested anymore in A, the counter will be 1 for all the time. So here we have a memory leak, unless we deal with these cycles. We are lucky, and CPython implementation has an algorithm and deals with cycles. So now I'll explain you how it's done. Okay? Again, we should look into the CPython code and the main structures that deal with garbage collection. Here we have basically what it is a double linked list of all the objects that are allocated in our program that is running, and essentially it's a double linked list of all objects, if I'm not wrong. So here, can you see? I don't know if you can see, right? Not so good, right? Well, in the cycle algorithm, we have different generations. So we don't have to execute the algorithm all the time, for all the generations. When is this algorithm executed? Once we reach some threshold that is set dynamically, depending on how our program detects more or less cycles, it executes or not the algorithm. Okay, so let's focus on the first generation. These are objects, the ones that I showed you before, this double linked list that has some counter. This is the counter, or probably a flag that says this is a reachable or not reachable object. So okay, the algorithm works as next. In first place, what it does is update these references, this counter. Okay, so let's say this object has 2, 1, 12, 14. Then the next step is to, one by one, we have to subtract 1 for each other object that is in this double linked list. So we take this object and subtract 1, 1, 1. So we end up -2. With this thing, what we are doing is, okay, if there is a cycle inside this list, these objects are they are alone in some place. So if we subtract 1 by each one, if the count is bigger than 0, that means that someone external of this generation is referentiating this object, so it's reachable. If it's less than 0, they are unreachable outside of the world. So we update all the objects, and we classify between reachable and unreachable. Okay, so this is unreachable, unreachable, and these ones are reachable outside of this generation. So the reachable objects go to the next generation because they survive to the garbage collection cycle. And we have some objects that are not reachable anymore, so we can kill them? No. There are some things that we have to take into account when we are dealing with cycles, and that are a bit tricky. So wait, we cannot kill these objects because we have two problems. We have to deal with finalizers and weak references. What CPython does is what objects that are reachable for finalizer cannot be safely deleted because we can referentiate other objects, and it's a bit of a mess. So please don't use finalizers or sorry, yeah.
What is a
Underscore deal, yeah. So please don't use other mechanisms that we have to. I've never used a finalizer. So because there is a lot of problems when we are dealing with garbage collection on cycles, because we cannot. There is no safe way to delete these objects. So this can be considered as not collectible. So it's some kind of memory leak. Okay. And what we can do, well, so they are moved to a set of uncollectible objects, and we store some statistics to know how our cycle algorithm is working. Okay. And to deal with, okay.
So are you saying that?
Are you saying that by using a finalizer, you mean underscore
deal, yeah.
Okay, method on an object, that all those instances become uncollectible?
Depends. If they are in a cycle, they are most likely to be uncollectible, yeah.
Okay, thank you.
Because you are not safe to delete these resources because you can have references to other objects, and it's an edge case that is tricky to deal with, and core developers decide to, in some cases, not to collect that object. And the other edge case that we have to deal with is web references. I think, do you know what web references are? Yeah? Well, we can declare some, there is a module that we can declare a reference that is not a strong reference, so it's not counted in our reference count, and declare some callback or just like a proxy to our object. So we have to deal also with this object. What CPython does is basically once we find some objects that are unreachable and has web references, it only executes the callbacks, the ones that are reachable outside of the unreachable set. The other ones are just freed because we're not interested in it anymore. Well, I think this is about how CPython handles memory, but I think it's not so interesting in this talk. And I would like to show you how the C code is and how well documented it is. It's just 1 minute. Oops. Here I'm showing you the gc module.c in CPython implementation. And if you sometimes have any doubt about how things work or whatever, I really recommend you to go directly to the C code. And if you are more or less used to work with C, it's very well documented and it's a very readable C. So here we have the main. This is the algorithm that handles cycles. And well, what it does is, as I showed you before, it updates the references of our extract, subtract the references, so these counters are updated, create some lists, but as you can see, it's very well documented everywhere. We can read very decently this code, even if we are not proficient C programmers. Well, just as I want to tell you that go to C code and read it. This is very well documented. Okay. Well, as everything in life, it has some drawbacks, this approach. So the process that is incremental, so once we allocate and we don't need some resource anymore, if it's not in a cycle, this will be freed immediately. But as drawbacks, as you can see, detecting cycles can be tricky. The most tricky thing is dealing with finalizers and weak references. And also, we have some overhead on our objects. We have this counter. It's an integer that is everywhere around. It cannot be much, but we're working in, for example, in embedded systems, more memory, but this is not the case in Python. But it's a drawback also. And now I'll try to explain you how garbage collection works in PyPy. If you don't know PyPy, PyPy is an alternative implementation of Python. It's implemented in Python, or Python, basically. In average, it's more performant than CPython. And on Sunday, I'll be giving a talk about how PyPy is built. So if you want to come, I'll be giving another talk. And now we'll explore how PyPy deals with garbage collection. One of the cool things about PyPy is that it's agnostic to the garbage collection. We can plug different algorithms to the runtime because it's not tied like in CPython. In CPython, this counter that is in our Py object, and it's difficult now to change to another way of dealing with memory. So they have been trying different implementation over time. They started like I think 10 years ago, and garbage collection has been evolving. Nowadays, by default, it uses incremental minimark. So, but if you want to try another garbage collector, when you translate PyPy, you can choose different ones. It's pretty cool, I think. Over time, they noticed that we allocate short-living objects all the time. For example, here we have some examples. In a for comprehension, let's say that we have 1 million elements. The life of these objects, that element, for example, is very short. We create a new one when we are element by 2. This is a new object, so the life of this object is very short. They like to be less. They like to live less than other objects. And here we have some. Even when we do method dispatching, we are allocating more objects. So they get this concept and they try to implement a garbage collector that deals with giant objects more performant than other approaches. Sorry for the drawing. I didn't have time to redraw because I've been changing this presentation this morning. I shouldn't do that. But this is how PyPy memory is allocated. We have in one place a place for giant objects that basically has what they call nursery, that is almost 4 kilobytes. And for the giant objects that don't hold in the nursery, there's some space in the heap for them. And then we have the space for all objects that are arenas with pages of different size that holds objects of the same size. Okay, so we have 2 spaces of memory on PyPy. One for the giant objects with the nursery where giant object lives, and also a bigger space for bigger objects, and then objects are moved to arenas when they live enough. So how does incremental minimark work? They do minor and major collection. What I mean with minor collection is they go through the nursery and they try to allocate the objects that live there. A major collection is basically a mark and sweep algorithm of garbage collection. So they mark objects and the all life mark and sweep. I'll try to explain you a bit how minor collection work, because I think it's the most interesting part of PyPy garbage collector. And well, as I told you before, objects tend to live short periods of time. So once the nursery is full, that is all the time because it's a small space in memory, they do a minor collection. Okay. So what does mean a minor collection? We go through the roots because we know in PyPy we know what are the root objects of our living program, and we go through all the objects that are referentiated from the roots on nursery. Okay, one, and we mark them, and they can be pinned. So it means that for reasons of performance, internally we can pin an object and say you have to live one more cycle in nursery, because for some reason it's more performant not moving this object to the old space. So we mark all the reachable objects on nursery. Also, we have to take care about pinned object because this is a special case. And if we mark an object, we have to allocate memory in the arena, in the all space for objects, and allocate and copy this object and move to. And the objects that are not marked, are not visited, we have to free. So this is why I put here in the slide that objects are moved only once, because they are moved, if they live enough, they are moved from the nursery to the old stage. Okay? And once we reach some threshold, we do a major collection that basically is a mark and sweep algorithm. Okay? We start on the roots, we iterate, we traverse the graph, we mark. This is the mark phase. This keeps unmarked. So, and the sweep phase, what it does is deletes all the objects that are not marked. Okay? So, how does PyPy deals with finalizers? This is how it works. It's something like steam machine. It scans that is iterating over this nursery, mark, sweep. At the end of the collection, it executes the ones that are alive. It's another approach of doing that. And well, the pros of this approach is that it can collect cycles by default. We're just traversing a graph. And drawbacks, basic mark and sweep implementations stop the wall. So it means that when we are doing a major collection, our program is stopped. So this is a drawback. And I think I am a bit in a hurry. I'm finished. I want to remind you that this year we are having NeuroPython in Spain. So if you want to go, you have to go. And do you have questions? I've been a bit quick, I think, but.
Excuse me, there was something in the beginning that I didn't really understand, and I didn't want to interrupt you. When you were talking about CPython, the implementation in CPython, you talk about reference counting first, and then another method to detect cycles. Are those implemented in CPython both?
Yeah.
In the same code? It's one monolithic code. Why PyPy has pluggable? Is it correct?
The approach is different on PyPy. PyPy is not meant to be only a Python implementation. They built a set of tools to create dynamic languages interpreters. So in their design, there are more flexibility about changing things. That's the reason. And it's not tight, for example, like in CPython, you have PyObject and changing the model is
those two ways of doing things are you have to use one or the other, or they both use by default?
Do you mean on
The reference counting and
yeah, they have to deal with cycles, because one of the problems of reference counting is, if you look into the example, look, here we have an example, right? The reference count here is 2. Once this object doesn't referentiate A, this never reach 0, because this is 1, this is 1. They referentiate in a cycle. So in CPython we have to deal with this kind of memory leaks, because if we don't deal with this, this is a memory leak.
is manual.
No, it's what I explained. It's like we have a double linked list with all the objects.
Okay, and this is implemented in
CPython. Yeah.
Okay, thank you.
Probably I didn't explain clear enough.
Other questions?
I have a question about the parallel, because I'm not expert of Python internals, but for example, the JVM, Java Virtual Machine, have several implementation of the garbage collector, like parallel. I don't know if you can explain some difference if you know.
I'm not an expert on JVM, but as far as I know, it supports parallelism by default. In Python implementation is not. We have GIL, Global Interpreter Lock, and also it has a lot of problems. This is all, for example, this double linked list is a global object that has all the references for the object. We will need to be thread safe and deal. Well, I think it's not possible to. I'm not an expert in Python internal, but I think it's not possible to have parallel garbage collection.
Other questions?
Yes, I have a question about the resources of the process internal. Is it using the same thread of the applicative code, the garbage collector algorithm, or is it instantiated a different one, specific?
I'll say that it's use the same.
Hi, nice talk. I was thinking about, is there anything that inhibits you from doing stuff like declaring dynamic extending of objects so that they are stack allocated instead of heap allocated if you know their extent is relatively short? I mean, is there anything in Python? I've been programming Python only for a few months, so I'm not much into it.
Everything in Python is allocated into the heap. It's dealt by the Python memory manager, and as far as I know, everything is into the heap because you don't have any information ahead about a program. Well, you can, but yeah.
Okay, I see. Thank you.
Would you recommend any practice for developing code that helps the garbage collector in case you know which one you're going to use, or is it bad practice?
Don't
Just
use
leave it to go.
finalizers because it can be end in an uncollectible, at the end, a memory leak. And if you have a problem with memory leaks, try to debug it. You can do, there are a module on standard library that gives you some information, but if you don't find the problem, just run Python with GDB. This is the most extreme cases. But try to avoid finalizers, my advice.
Other questions? Okay, so thank you, Francisco.